Foundation, I would like to welcome you to this year's prize award ceremony. I would especially like to welcome laureates and their families to this ceremony, whose purpose is to honor the laureates and their contributions to science and literature.
Yeah, and now time for David Wineland.
I think the thing that has always interested me and continues to interest me is that even when I was first exposed to physics in my high school class, what I liked about it was that relatively simple math, at least simple for mathematicians, can be used to explain how the world works. And so I would certainly put quantum mechanics into this relatively simple math. And what I like, or certainly one of the things I like, is just the fact that when we do our experiments on these quantum systems, these atoms, we can use quantum mechanics to explain, what goes on in the experiments, and this connection between the theoretical explanation and actually doing the experiment is still, I still really like that aspect. So. We're always trying to find ways, of course, to improve the clocks, and sometimes that does involve stepping back and saying, well, where does, we can't use the standard practices to do things. We need to try to invent new ways to do that. A good example of this is when I came to NIST after a couple of years being here. My boss at that time, Helmut Helvig, was able to get us some money to try to do laser cooling. And laser cooling is important because one of the effects that shifts the observed frequency of the atoms that we look at is the so-called time dilation shift. And this comes from Einstein's theory of relativity, where time for moving objects goes slower than it does for stationary ones, and this effect occurs at a very small scale with the atoms that we look at, but it's an important one, and we have to correct for that. So, one of the other areas we've been exploring is the idea of making a quantum computer, and it turns out that one of the fortunate things is basically all the techniques we use for clocks are applicable to trying to manipulate atoms for a quantum computer. To implement the ideas of making a quantum computer, it turns out that we need to have an extreme form of cooling. So we basically have to completely freeze out the motion of our trapped ions, only limited by the limits of quantum mechanics. That is, we put them in their so-called ground state of energy. And this was this level of cooling wasn't so necessary to achieve the accuracy that we needed for the clocks, but it was critical to be able to manipulate the atoms to try to make them as quantum bits or qubits. And so we had to develop a technique, and we're first to demonstrate that we could actually put the atoms in the ground state of their motion. With this idea of superposition, we can put our atoms, our ions, in these states where they're simultaneously both a 0 and a 1 at the same time. Now why this gets interesting is in this superposition sense, we can, with 300 bits in a classical computer that could store maybe a line of text, our quantum computer that can store more has more memory elements than if we took all the matter in the universe and made a a classical memory that way. So it's this exponential scaling that gives this potentially very high ability for memory, and also turns out that we can operate on all these bits, all these numbers at once with a single operation. So in some sense there's this property of massive parallelism, and that's what we're trying to take advantage of. Quantum computers are not going to replace classical computers. In fact, we already need a fairly sophisticated classical computer to run our simple quantum computer. But there are certain specialized problems. And around 1995, Peter Shor, a computer theorist, came up with the idea. He showed that if you could make this quantum computer, he came up with a computing algorithm where you could efficiently factorize large numbers. Well, that may sound a little esoteric, but basically all modern encryption systems, when you buy something with your credit card on the web and it's encrypted, basically all these encryption systems would be compromised if you had the ability to efficiently factorize large numbers. But what's I think more interesting for scientists is the application, physicists in particular, is the potential application that we might use this, even a small quantum computer, to simulate other quantum systems. So an example would be of this, maybe popular today and timely today, is that people are all excited about seeing the Higgs particle. These particle systems are already so complicated. They may not involve more than tens of elementary particles, but there are so many particles that we don't have. Our classical computers can't solve the quantum dynamics that goes on in these systems. And the fact that we're more generally trying to develop methods of metrology, measurement, that are limited only by quantum mechanics. So, that our work on trying to make a quantum computer, everything we need to do that for those experiments also improves our ability to do metrology.